Greetings, physicists. Today we're going to be talking about graphs that yield straight lines, and if you have a graph that doesn't yield a straight line, how do you make it look like one? So this is the topic of regression analysis. So we're going to start off with some data. We always start with some data. So let's say you collected the following. Oops, let's get rid of that. Let's make that a solid line. Let's say you start by taking the following data table in lab. You've got some distance data, some time data, right? Really some position data and some time data, right? And you've got these data points. At time 0 seconds, something was at 3 meters. Let's do this in meters and seconds. And we'll go 5 and 1, 7 and 2, and 9, and 3, and 11, and 4. And you can probably already see the trend here. And 13, 5, 15, and 6. Nice trend there. And we're going to graph it. So let's just talk about graphing rules since we haven't yet. You may have already seen this in your math class, but when you graph, you want to do it on graph paper because, like you can see me doing, I am very bad at drawing straight lines. And so the graph paper will evenly space your lines out. Now for me, I'm going to look at these data points, and because I've been doing this for a long time, I almost always label my y-axis to be position and my x-axis to be time. But basically you want your independent variable on the x-axis and your dependent variable on the y-axis. And I'm looking at my t column here. And I see that we go up to 6. So this should be pretty easy on this set of graph paper. I think I can do it every 2. So 1, 2, 3, 4, 5, 6. That's pretty good. If I tried to do it every 3, I think I would run out of marks before I got to the end there. But you want to use as much of the graph as you can. That's another trick for graphing. And because you'll see the shape easier. Now with my x column, it goes all the way from 3 to 15. Let's see here. 3, 6, 9, 12. Yeah, I can do that on here by 2s. So we'll go 3, 6. Pretend that I'm doing this at the vertices. 9. Again, if you're freehand doing this, you tend to have, let's call that top one 15. That's fine. And I'm going to go ahead and label this. I said earlier I want to do this in seconds and meters, but this should really match what you took your measurements in. We were assuming meters and seconds over here. And our particular graph starts at the origin. That is not always necessary. But in this case, it's not going to hurt us to start at the origin. The times when you don't want to start at the origin is if you're going to have a large blank section of a graph. So if my origin was over here somewhere, or if my graph, starts halfway across because I don't have any data points before like 3 or something, let's just start at 3. Because again, the point is to fill the graph up. All right. And we can label it, this is position versus time. Vertical versus horizontal is how you label your graphs. So this is the basic part of every graph. You're going to label it up. And hopefully when you draw your graphs, you have a straight edge handy. I'm trying to do this on my iPad, so I'm not really putting a straight edge up to it. And that's why my graph looks so messy. Okay, let's put in our data points. 0, 3 is a data point. There's 1. And then, of course, I didn't mark these, but that's 1, 2, 3, 4, 5, and 6 seconds. So I've got 0, 3. I've got 1, 5. Ooh, that's going to be fun. So 4.5 is halfway, so 5 is going to be a little past halfway, but it won't be, well, it should be a little below that. Yeah. 2 is 7, which should be just past the 6. So we'll do it like here. I think a third past the 6. 3 is 9. That's a nice vertex right there. 4 is 11, again, past the midpoint, because the midpoint here would be 10.5. Oh, it should be down in the lower half there. Whoops. Just doing a quick and dirty graph here. 5 is 13, so I gotta go above the 12. All right, let's do it. Oh, no, 1 over. Good idea to graph in pencil. And that way you can fix those kinds of marks. And the 6 is a 15. Here we go. Right there. All right. Now, a true graph, if I put my data points like this, you're going to use a straight edge and do a best fit line through your data. But you can see that this looks very linear. This looks like a straight line graph. Maybe there, and if you look at it mathematically, it's actually a perfect straight line. But even with my drawing, it looks linear. So I'll go ahead and, again, pretend that I connected that properly. And then we can just take a slope. So really what we're interested in, this graph here follows the shape of this function, y equals mx plus b. And you're going to want to know, I'm going to show you 4 different types of graphs today, and you're going to want to be able to recognize their shapes and match them with their functions. So y equals mx plus b for this graph, and in our case, that's going to be y equals slope. Now, I wrote m. I'm going to actually change that. Can I erase? Maybe I can't. Okay. So I'm just going to change that to say y equals kx plus b. I think k is more commonly used by physicists instead of m. It doesn't matter. They're both just, it just means the constant that the slope is multiplied by. So it's the slope of the graph, excuse me. This is slope-intercept format. So slope times x plus the y-intercept. And for us, our y-intercept was 3. So I can actually put that into my equation, plus 3. My x values, oops, let's get rid of that. My x values here, when I do this in physics, I'm going to use what I actually graphed on the x-axis. And right there, that was time. So my x can be replaced with time. My y values, I knew what those are. Those were my position values. Now, that's a little confusing because we use x to represent position, but that's fine. So if this was a physics equation, we would say that x equals something times t plus 3, and that k value should be the slope. So let's look at my graph here. I need to take a slope of this graph. I can take any 2 points that are on the line. Now, the way I've drawn my graph, I only really have 2 points on the line, the last one and the first one. But because of the regularity of these data, if I had drawn this with a straight edge, you would have seen it went through basically all the points. But I'll go ahead and be a good physicist and say that this point is valid because it lies on the line, and this point is valid because it lies on the line. If you had a true best fit line with a straight edge and it came out the way I drew it here, don't ever include points that don't lie on the line. Mine's a sloppy drawing, but if you have a true best fit line that goes through your data points, don't use them. And also, if I had tried to draw this as a true best fit line and came out with this, I would get points off because a true best fit line would have about as many points above the line as there are below the line, and here all of my data points are below the line, so that's not a very good best fit. All right, that's for another discussion. So let's do our slope. Our slope is going to be, so k is our slope. K should be delta y over delta x, rise over run. Or in this case, that's the same as saying delta x, because that's our vertical axis, over delta t, if I'm using the variables that represent these axes. And delta is always a final subtract an initial. So if I do the top values, the y value up here is a 15. The y value down here is a 3. The x value up here is a 6. And the x value over here is a 0, if we're doing xy notation. All right, so the y value here, so we have 15 minus 3 on top. That's our delta y, or in this case, delta position, which is really a delta x. And then we have our 6 minus 0, which is our delta t, equal to 15 minus 3 is 12 over 6. That's a slope equal to 2. And I'm going to come back down here, put it in. That's 2. So in here, the position was equal to 2 times the time plus 3. And if you're analyzing this graph, that's the slope. And the slope here is how fast this thing was moving. That's really the speed. And then the 3, the intercept, that's probably because the person didn't start at the starting line. If the starting line was 0, he started 3 meters ahead of it. He got a little head start before we started our timer. That's what that means. And you could even give units to the slope. The slope was 12 on top, and on top was meters, and it had 6 on bottom, and that was seconds. So that was a 2 meters per second. That's how fast this person was going. So that's the basic idea with the graph. But that's not really the whole purpose here of this tutorial. We're trying to teach you how to do linear regressions. So let's go and use some new data. Let's suppose you have the following data table. Let's see if I gave myself enough room. Again, let's suppose you are taking position and time data, meters. Pen, are you going to work for me? There you go, meters and seconds. All right, I'm trying to draw too tall, close to the top there. Meters and seconds. Let's do that. Try that one more time. All right, and let's give us this data. So this person does start at the starting line at 0, and at time 1.3 seconds is at position 1.7 meters, and then we get 2.5 seconds. He's at, or she, either way, 6.25. And then at 3.8 seconds, this person is at 14.4 meters. And at 4.3 seconds, this person is at 18.5 meters. And at 5.9 seconds, this person's at 34.8. And that's all the data we took. So I actually made the table too big. That's fine. So let's try and graph this now. I'll do the same tools I had before. Let's draw my graph. Again, you're doing this with a straight edge because mine's sloppy. And I'm still going to put my time here and my position here. That's usually how it goes, although this does depend on how you collect your data. My time axis goes basically up to 6 again. We're really ending around 6 seconds, even though they're decimals. Now, I could try and do it 5.9, but subdividing that is very difficult. So to make it easier, let's go 6, and let's see if I have 3. Yeah, I think I'm going to go by 2s again. Come on. 1, 2, 3, 4, 5, 6. So I'm going to label it like this. It would be a mistake for me to label this with the points from this column here. If I were to write 0, 1.3, 2.5, 3.8, because these values are not evenly spaced. The distance between 0 and 1.3 is 1.3. The distance between 1.3 and 2.5 is only 1.2, so that's not even. And from 3.8 to 4.3 is like 1.5. So because these values aren't evenly spaced, I can't really use them. And you'll see a lot of amateur graphers, if that's such a thing. I guess we're all amateur if we're not getting paid. But a lot of people who I will see people turn in graphs, students turn in graphs that have tried to use their data points as line markings on their graph, and that's just not good. Don't label your axes with your data points. All right, do the vertical axis now. We go up to pretty close to 35. And so that's 7 spacings of 5. I think I have room for that. 2, maybe 1, 2, 3, 4, 5, 6. I will have to go a little higher here. Fortunately, I can just barely do that. So there's 5, 10, 15, 20, 25. That's going to be 30. Sorry, it overlaps with the x. And that's going to be 35. Again, this is meters on this axis. This is seconds on this axis. Good, and we're still doing position versus time. Almost looks like pressure versus temperature, doesn't it? That's cool. Okay. Let's plug some of this stuff in. So 0, 0, the origin is on our graph. And 1.3, 1.7. So 1.5 is right here. So I'm going to be a little bit past that. Now this would be 2.5 here. So I have to go almost halfway up this first. So it's going to be something like right there. Is my guess for where 1.7 is. And then I have 2.5. That's a nice, easy halfway point right there. And I have 6.25, so that's past the 5. If I was here, I would be at 7.5. So 6.25, I think, is exactly halfway between 5 and 7.5. Yeah. So if I'm halfway here and halfway between 5 and 7.5, so that's right about there, I believe. Let's say that's true. Then I have 3.8 up to 14.4, so 3.8. So this is 3.5 right there, and 3.8 would be just past halfway, so maybe right there. Up to 14.4, that's very close to 15, so this is 12.5 right there. I think that's going to be pretty close to right up there, so let's see if I can mark those together. So almost up to this 15 line like that. Sure, let's call that my point. Not a very good point, is it? All right, then we have 4.3 to 18.5. So 4.5 is there. So just before 4.5, maybe halfway there, up to 18.5. So this is 17.5. So not quite halfway between 17.5 and 20 is where we're going. So maybe here. That's a little too high. All right. And then we have our last one is almost 6. It's very close to 6. If this is 5.5, it's 4/5 of the way between that and 6. So almost to the end there. There are actually lines on this graph paper, but the tool I'm using to draw on the iPad with is so wide I can't really fit it in there. It's wider than those lines are. So 5.9 up to, again, almost to 35, which I realize I need to move the title of the graph because it's going to be in the way. PVT. All right. Up here to 35 over to, so this is like really right about there. Now this is data you couldn't really draw a best fit line to. It almost looks linear, except for the first couple of points. The first couple of points really give this away. There, this point, this point, this point. Look at that. This is pretty clear. If I were to draw a best fit curve through this is fairly parabolic in shape. So when I look at it, if I was going to make a function for this, the function it resembles would be a y equal, not mx or kx like we used before, but more like a kx squared plus b. This is a power curve, a quadratic, if you will. So let's change that to look like a physics equation. The vertical axis again had position on it, distance, equal to k is our slope, and you can have a slope of a quadratic curve. I mean, x squared function certainly has a different rate at which it increases than a 2x squared function. If you draw them on the same graph, you will get, two different increasing values. So it's just not a straight line thing. It's you can't do a delta y over delta x to calculate it. So kx squared, and in this case, oh, I did that wrong. We were actually measuring t on this axis, so kt squared. And in this case, the b is 0. So this is our function. And it's hard to get that k value. To get a k value, you really need a linear function. So we want to try and make this look like a linear function. Well, let's do some algebra here. If I want to isolate this k, I can divide both sides by t squared and get x divided by t squared equals k. So as k increases, t squared increases, and they both do so at a constant rate. So if I want a straight line out of this, and x over t to be a constant, or an x over t squared to be constant, I have to actually graph that. I have to graph x, and I have to graph t squared. So I need to rewrite this. I'm going to make a new data table. X is going to go in that data table, but the other column is going to be t squared, because that should give me a constant. Well, I'm just going to copy my x values over. That's 0, 1.7, 6.25, and 14.4, and 18.5, and, oh, come on, 5, and 34.8. But I can't just copy my t values over. My t values, if we go look at them, are 0, 1.3, 2.5. I'm actually going to have to square those to get what I need here. So let's do t squared. 0 squared, all right, is 0. 1.3 squared is 1.7. Well, that's interesting. 2.5 squared is 6.25. Interesting. And as I bet you can see the rest of the pattern here. I chose these numbers on purpose so they would work out like this. But these were in fact squares of each other, so 34.58. So when I graph this, unsurprisingly, this will definitely turn out to be a straight line that we can take a slope of. And I'm going to go ahead and do a real quick one, because I know it worked. 5, 10, 15, 20, 25, 30, 35, 5, 10, 15, 20, 25, 30, 35. But, I mean, you can see 0 is here, 1.7 and 1.7 is going to be here, 6.25 and 6.25 is going to be here, 14.5 and 14.5 is going to be about here. Again, I'm rounding. 18.5 and 18.5 is going to be here. And 35 and 35 is going to be up here. And the straight line, again, use your straight line tool, should go through all of them. I did that rough with no numbers. Trust me, you can graph those, you'll get the same stuff. So again, but the axes change. So this is distance, that's position in meters, right? 0 to 35 meters. This is now time squared on the horizontal axis, and it's going to be in seconds squared. That's your unit, all the way up. And because we got a straight line out of it, you can now pick 2 points on the line, any 2 points, and you can take the slope. Now, because I jiggered the numbers so that they would work out perfectly, we are going to have a slope, a k value equal to 1, because the top and the bottom should be exactly the same values. But notice the unit on it. It's 1 meter divided by a second squared, meter per second squared, or meter per second per second. That's an interesting unit. It is appropriate in this case. So the slope of this line, this business here, tells us that there's a change going on of 1 meter per second divided by second again. That's an acceleration. That's like saying I start at 1 meter per second, then the next second I'm at 2 meters per second, and the next second I'm at 3 meters per second. This person is getting faster at this constant rate. So this is an acceleration that we just were able to get from this graph. Good times. So totally useful to be able to do these linear regressions. we started with a graph, and the way we were able to make it work, we graphed it out and got this curved slope, this quadratic, and we recognized that a quadratic is a kx squared plus b, and that to get a slope of that, we would have to take an x versus t squared graph. And so here is our x versus t squared graph. And that gave us the slope we needed. All right. Two more types. We're going to do two more types of graphs. And I'll try to get through them as fast as I can. So the next type, let's get some more data here. So we're going to graph this one. Here it is. Oh, go gadget pen. We have, again, position and time data. And we'll say that we start at the origin again, and it's 1.4 and 2 seconds, and it's 1.7 and 3 seconds, and it's 2.2 and 5 seconds, and it's 2.4 and 6 seconds. These are meters and seconds. And then it's 2.6 and 7 seconds. This is the data that someone supposedly took for a moving object. And we're going to graph that data up. Here it comes. Give myself some more room this time, and maybe I won't run into the title. Bottom set of data, the seconds, looks like it's just going to be easy to go from 1 to 7. So 1, 2, 3, 4, 5, 6, 7. Top data goes up to 2.6. I could go to 3, but think how crowded that's going to be. There are 1, 2, 3, 4, 5, 6 data points between 0 and 3. So if I actually want to spread that out a little bit more, I would like to put 3 near the top somewhere. So let's just 2, 4, 6, 8, 10, 12, 14. So there are 15 lines on my graph if I go from 0 all the way up to here. So if I start at 3, then every 5 lines, 1, 2, 3, 4, 5, that's 1. 1, 2, 3, 4, 5, that's 2, 1, 2, 3, 4, 5. So that gives me a lot more space to work with. Also, that means that every single little line is a 0.2, and that's a nice easy subdivision, especially here, and then halfway between one of those lines is a 0.1. So I can visualize that, and a lot of my values are there, like 1.4 is going to be right on a line, and 1.7 is going to be a halfway, etc. So I think that's good spacing for me. So let me do these 1, 2, 3, 4, 5, 6, 7. Good. And again, this is meters or position, and this is time in seconds. So, quick plot. I am starting at the origin. I am going from 1.4, so that's 1.2, that's 1.4, all the way up to 2. Good, that's on a vertex. I can do that. I have 1.7. Here's 1.6 and 1.8, so halfway between that up to 3. Here's 3. And then I have 2.2, which is right here, up to 5, which is right there. And then I have 2.4 up to 6. There's 2.4 all the way up to 6. And then I have 2.6, which goes up to 7. Now again, if you just consider the last couple of points, they look a little linear, and part of that is because I rounded my answers when I created these numbers, but if you take that origin into effect, this really does have a trend of a square root function. So that's position versus time again. So a root function, what does that look like? Well, a root function would be y equal to k square root of x plus b. And again, our b for this particular graph is 0. So the y-axis was position in meters, so the position by x, and then k is our slope, or our proportionality constant, and then square root of x, but on the x-axis we had time. So our function here will be y, or position equals k times square root of x. So if we do a little algebra, we get x divided by square root of time should equal a constant. So if x increases and the square root of time increases at the same rate, we will get this k value. So what I really need for a constant slope on my graph is to graph these things, position versus square root of time. So I'm going to have to make me a new data table just like I did with the other one. So here's my new data table. Oh, excuse me. My new data table should be position. That's not changing. And my position values were 0, 1.4, 1.7, 2.2, 2.4, 2.6. But I have to graph it with the square root of time as my x-axis. Well, the square root of 0 is 0. The square root of 2 is 1.4. And you will probably see the same pattern you saw when I tried to do this with the power curve, that I have again made the numbers easy so that when we graph this, when I go back and graph it, we should see another perfect straight line with slope equal to 1. Now sometimes this will be, especially if you're using data you collected in the lab, your lines will not look so nice, but you should get something that generates a best fit line that shows a linear relationship if you really do have data that were originally in a square root relationship. Now, in this case, my position is still on the y-axis and it's still measured in meters, but on the x-axis I have the square root of time, or square root of seconds, as my unit. So this would be meters per root seconds, which is not a very common unit, so maybe this would be rough for you. Okay. That's the third shape you're going to want to be able to use. This one comes up, for instance, usually in the other direction with pendulums and springs, because the relationship between the period of a pendulum and its length, for instance, the length of its string is a square root relationship. And with springs, it's a similar relationship, but with its mass. All right, let's keep going here. Let's do one more. This time we got a set of data. Here it is. Position, time, data. And we've got 0.33 and 3. We've got 0.20 and 5. We've got 0.08 and 12. We've got 0.05 and 20. We have 0.04, which is 25, and 0.02 corresponding with 50. And again, we'll say that this was in meters and this was in seconds. So at those times, we were at those positions. And we graph it. Now, this one can be tricky to graph, especially these data. I'll go ahead and do the time axis first, the time in seconds. I'm going up to 50. And the smallest I get is, looks like a 3. By 5s would probably make sense. Let's see if I have enough room for that. 4, 5, 6, 7, 8, 9. If I go all the way, here we go, watch this. Magic. If I go all the way here, there, and make that 50, and that 40, 30, 20, 10. All right, that's not too bad. Again, pretend the 0 is on the vertex, and it goes all the way there. Okay, and then for the vertical axis, okay, the vertical axis is the tough one. We'll have the smallest is 0.02 and the largest is 0.33. So I'm going to treat this, here's how I'm going to do. I'm going to do this the way I did the 35. So 5, 10, 15, 20, 25, 30, 35. Except that instead of making the top 35 like this, I'm just going to move the decimal twice and put it right there. And then same here, 0.30 and 0.25 and 0.20, etc., etc., etc. And I'll get down to 0.05. Don't forget to move that twice. And so now what you can see is that halfway between 0.05 and 0 should be like 0.025. So we're getting pretty close. And that should make these easy enough to plug in here. All right, let's start with 0.33 and 3. So if this is 0.25, which is halfway, and halfway, oh gosh. Yep, you probably noticed it before I did. This is a no-no. That's a three spot distance. No worries, I have an eraser. At least I think I have an eraser. There, is it going to let me? There you go. So we're just basically, keep all those vertical marks. We're just going to redraw that line here. That beautiful, almost straight line. Everything should work out. Yeah, perfect. Okay. So now that everything is actually okay. All right, so 0.33. So halfway between 0 and 5 should be 2.5, so 3 should be just above that, and 0.33 should be just above that. So it's really right about there. Okay, we have 5 and 0.2. 0.2 should be just below the halfway. Remember, the halfway is 0.25, so 5 and 0.2 should be like right there. Excuse me, 12 and 0.08. Oh, I did this wrong. Bad. 0.33, not 0.033. 0.33 is way up here. 0.33 and 3. See, you can do this a long time and still make mistakes, which you will learn by watching my videos. Here you go. That's more like a starting point. Okay. 0.2 and 5. Ooh, that's right on the line. I like that. 0.2 and 5. Okay, much better. 0.08 and 12. Well, that's going to be 0.075. So 0.08 should be just above that, and 12. So if that's 15, this should be 12.5. So it should be just behind that. So behind 12 and above 0.07, which is right about there. Sure, let's call it right there. All right, 0.05 and 20. 0.05 and 20 is right on the line. Love it. Right there. 0.04 and 25. So this is, again, 0.25. So 0.04 should be 4/5 of the way up. And 25 is right on the line. So we're right there. And 0.02 and 50. Okay, so just below the halfway point. Right there. Okay, so this data, look at it. If I draw a line through it. Yep. That's a pretty recognizable curve. That's a hyperbolic curve. So again, don't forget my title, P, position versus time. So this follows the following. This would be represented by the following function. This is a y equals k times 1 over x plus b. Actually, I don't know if there's an intercept. I think hyperbolic functions don't intercept. Let's just get rid of the b. This is a k times 1 over x function. There you go. And in our case, the y value was position times or equal to k times 1 over the x value, which was time. Now, if we do a little algebra and we divide the 1 over t to the other side, now here's the problem. If you do that and you simplify the function, you're actually doing yourself a disservice. You will get, this is the unsimplified version. X divided by 1 over t should equal a constant. Well, some people will go, oh, let's resolve that and put the t up here next to the x. X times t equals k. That is mathematically true. That is not going to help you set up your axes to make a straight line. If you really want this to get a straight line function, you need to recognize that as x increases, 1 over t should increase at the same rate in order for you to get that constant. So, we're going to do it like this. I'm going to just graph those. I'm going to make my new data table, and I'm going to do x like that, and I'm going to do 1 divided by t instead. And those will be my new values, and I should get a straight line. And if you've been watching the last 2 regressions, you will not be surprised to learn that my numbers work perfectly. But that's just for the purposes of showing you. All right, 25 and 25. Pretend that 25 looks nice. Here. 50 and 50. They don't let you become a physicist unless you have really illegible writing. That's my defense. So, we keep going. If we graph those, yes, you will definitely get a slope that's nice and straight, because in this case I have a slope of 1, but that's a position here, and that's a 1 over time on this axis. So with those 2 axes, I will get the straight line slope that I need. And that straight line slope will be a delta x and then 1 over delta t. So that's a meters here, and that's a per seconds here, or a hertz. And so you would have your k value equal to 1 meter over 1 over seconds, or 1 meters times seconds. 1 meter second. This inverse relationship comes up specifically in waves. You'll see this. The relationship between frequency and period, for instance, is an inverse relationship. But it's not the only place it comes up. So those are your 4. And I'll give you a quick recap, because this video has already gone kind of long. Linear functions. Easy to get. You can already get the k value if you have a linear function. That's just y versus x. So it's a delta y over a delta x. If you have a quadratic function, okay, so let me just, that was y equals kx is the function described by that line. If you graph your data and you get a function like this, this is a y equal kx squared function, and you have a hard time taking the slope value because the slope, of course, is always changing. So what you do, so this was y and x, so you're going to regraph it as y and x squared because, of course, you had an x squared, right? And when you do that graph, you should then get linear data, or a linear graph, and then you have the k value equal to y divided by x squared. The delta y or the delta x squared anyway. All right, that's that function. If we keep going, if you had this shape, watch for these shapes, if you get that shape, this is a y versus x, and the function described by that is y equal k square root of x. So to get a linear function that you can actually take the k value of, to get something you could take a slope of, the whole point is to try and calculate that slope. You regraph it as y versus square root of x, and you get a k value of y divided by the root of x. And lastly, if you get this shaped curve on a y versus x graph, a hyperbolic curve. That is a y equal k times 1 over x. So regraph, keep your y values the same, change your x values to 1 over x values, you will get a straight line, and your k value will be equal to y over 1 over x, or yx. Okay? You will, at some point during the labs throughout this year, get versions of these graphs. You'll probably get a lot of the quadratic functions. You will get some square root functions. You will get at least one hyperbolic function. And in order to be able to calculate the slope or the k value for your graph, you will have to make one of these regressions. So practice, 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 so that you're ready to do that when your data comes.